Hi everyone, good afternoon. Uh, yeah, uh, this is basically I'd like to present on a thermal performance of a school building in a temperate climate using retrofit passive strategies. This is basically a dissertation work of a graduate student, Shveta Mohan. So I'm presenting on her behalf as she could not travel due to financial constraint. Uh, Basically, achieving thermal comfort is essential in improving the health and well-being and also improving the productivity. Basically, a balanced combination of building and systems in line with the local climate uh, helps in achieving better thermal comfort, especially in temperate climates. Um, the weather conditions are favorable for throughout the year. However, it is possible to achieve thermal comfort using passive strategies without dependence on active measures. And the design challenge here is to reduce the heat gain and reduce the heat transfer into the interiors and also increase the heat loss by ventilation. And this is possible if it is in a new building. However, in an existing building, there are a lot of measures that need to be considered. Here, basically, the aim is to assess the thermal performance of an existing school building, and this was done through analyzing the passive strategies that are suitable for a particular climate and also the strategies that have been adopted in the existing building were assessed for its climate suitability. Then the heat gain was of the particular building was assessed by means according to Scully, and then the parameters that contributed to the heat gain were assessed. Then the retrofit measures were suggested based on the percentage decrease in terms of heat gain. So that were proposed based on that. A school building in Bangalore in Whitefield was chosen for the study with an area of about 1,500 square meter, and it is a G plus one structure. We have northern side, the southern side, and the eastern side as a G plus one structure, which has got classroom. And this is a view of the school wherein you can see on the western side we have a temporary building which is a multi-purpose hall, and the southern northern side we have G structure with classrooms which has got a wired mesh so that the air continuously passes through classroom from the surroundings. So there is the interior of the building doesn't have a climate barrier. It just have the hot wind from the outside continuously enters, resulting higher heat gain. And the block on the southwestern direction also block the southern winds. In order to analyze this, first we performed a climate analysis. We tried to understand the weather parameters annually and found that during summer between March to June, because of higher air temperature and higher radiation, shading becomes essential in order to reduce the heat gain. Uh, and other times like December to February and July to November way comfortable because being in a temperate climate. Then the thermal comfort analysis also revealed that the comfortable hours in terms of ASHRAE is 34%, but this could be increased significantly by means of retrofit strategies. We did then the temperature of March, the summer period was analyzed, especially during the working hours of the school. In the early morning, as in summer, the temperatures were microclimate were significantly comfortable, wherein during the start of the school from 9 to 12 noon, because of the intense radiation, the winds become very hot and the entire indoor environment, because of the porous nature of the envelope, it became very uncomfortable. And in the post lunch session between 12 to 3 p.m., also uh, the because of high radiation, the hot winds, the intense heat gain happened. So then the shading analysis was done. This also revealed The central courtyard, which was covered with paver blocks, increased the heat gain uh, because of its exposure to solar radiation throughout the day. Um, Wherein in winter the courtyard is completely shaded, so it provided comfort. So this indicated the shading of the courtyard throughout the day is a significant element. Then we also performed shading analysis to analyze the depth of the shading devices in order to protect the facades from heat gain. Um, Further, the depth of the shading devices were calculated in order to protect the surfaces, the windows, the openings, as well as the opaque surfaces through shades. Then the form and proportion were also analyzed for all the blocks, and the surface to volume ratio, which is 1 is to 1, reduced the heat gain of the building. However, in the northern and southern block, the longer surfaces added on to the heat gain. Then we conducted assessed the convective heat gain of all the blocks, which were very high, and the convective heat gain as well. The conductive heat gain and the convective heat gain was very high here. So this revealed that the materials that are used for the roofs and walls need to be lower. It should be with lower absorption coefficient and better reflection, and the lesser percentage of glazed windows and the larger proportion of the opaque surfaces also added on to the heat, and the meshed corridor spaces or acted as a does not provide proper climate barrier, which increase the heat gain through convective heat gain. Um, so we moved on with calculation of passive retrofit strategies to with in terms of shading the opaque surfaces as well as the windows. A reduction of 48 to 52% heat gain was found, um, especially on the upper floors, which are not shaded by the surrounding building, which are in the southern facade and the eastern facade. Then the mesh area was replaced with bamboo fins, which adjustable bamboo fins, which can regulate the lighting that entered the surfaces, and it also avoid glaze. So there were two options that were worked out with bamboo fin and a reflective white coat on MS film, and the bamboo fin reduced the heat gain significantly. 50% reduced the heat gain, and it also helped adjustable fins, which helped in adjusting the lighting levels because there were too much of light within the classrooms. And on the western facade, the vegetation reduced the heat gain by about 66%, um, and which could be an easy retrofit. Then the major heat gain was through the roofs, which was basically of the roof was made up of metal sheet, which really had a higher heat gain. So which was replaced. We tried replacing with five options, and we found that uh, two options worked out better, which is the roofs with a green roof on top of the metal roof, which acted as an insulation and reduced the heat gain by about 92%. And also, a roof material broken terracotta reduced the heat gain by 80%. Uh, the wall, the conventional brick wall, by introduction of internal gypsum board, reduced the heat gain by 43%, and the uh, clay tile cladding on the external side also reduced the heat gain by about 19%. Then modifying, since the courtyard was completely of paver block, it increased the heat gain, and the microclimate, the air temperature was significantly increased. So we tried working out a combination of soil, grass, open grid pavers with cedars and vegetation in the courtyard, which reduced the air temperature significantly by about 5 degrees Celsius. So it also this combination helped reducing the microclimate, and it really helped in improving the thermal comfort inside. Uh, so, with the various options that have been worked out, the green roof retrofit strategy is easier, which did not have um, a lot of interventions. It had a minimal interventions in terms of reducing the heat gain, and it also had a significant insulation property that could which could be laid on the metal roof, and with minimal intervention, this was more efficient when compared to a wall retrofit, or in terms of a shading retrofit in terms of cost. Thank you.